Everyone, in this video we're going to go over section 4.9, antiderivatives. So consider the following situations. A physicist might know the velocity of a particle, but they might want to figure out the position of the particle from that velocity. Similarly, an engineer might know the rate at which water is leaking from a tank, and they want to figure out how much water has leaked over a certain period of time. Or a biologist might know the rate at which a bacteria population is growing, and they might want to figure out how big the population would be sometime after that. In each of these cases, the problem is to find some function that we're going to call it a capital F. In all three of those situations, we're looking for some capital F whose derivative is that known function. In other words, we're looking for some capital function to model the position of a particle, to model the amount of water that is leaked, or to model the population of bacteria at a certain time, when all we know is information about its derivative. So, if we can come up with some capital F whose derivative models the situations that we were talking about, we call capital F an antiderivative. So let's state the definition of an antiderivative formally. So a function, and before I go on, I want to draw your attention to the fact that capital letters are important. For what we're doing today at the tail end of Chapter 4 and for what we go over in Chapter 5, there is a difference between a capital F and a lowercase f. Capital F is not the same as lowercase f. Or I'm probably going to write it in cursive. Capital F is not the same as lowercase f. Capital F is still capital F, and lowercase f is still lowercase f, but capital and lowercase mean something different. Okay, so a function f, capital F, is called the antiderivative of little f on some interval I if capital F prime of x is equal to lowercase f of x for all x in I. Okay, antiderivative. To set the record straight, antiderivative is typically one word. I have more often than not written it as two words. So a function f is called the antiderivative of this lowercase f. On i's, most of what we're going to be doing is going to be over the real numbers. On I, you can really take as over its domain. Though this isn't 100% true. For what you guys are doing now, we can really consider I to be the domain of that function. But note that it doesn't necessarily have to be as you progress through math. But just to kind of establish some intuition, a function capital F is called the antiderivative of lowercase f over its domain if the derivative of capital F is equal to lowercase f. Once again, for every value in its domain. So let's consider, what if lowercase f was equal to x squared? Okay? So can you think of some function whose derivative is equal to x squared? Well, it might help. We're going to be going backwards. It might help to think of the power rule. What is the derivative of some function x to the n? Well, its derivative, that power would come down, n times x to the n minus 1. So we should apply this idea backwards. Notice how when we take the derivative, the power comes down, and then we subtract 1 from the new power. The order is important. Power comes down, then subtract. So, what we want to do is we want to do the opposite of what's being done in opposite order. So, our capital F of x is going to be, we would need the power to come down, and then we would have, the order of operations, not really order of operations, but taking the power rule, power comes down, 1 goes away from the top. So in opposite order, we want to add 1 to the top, and we want to divide by that new exponent. But it's true that f of x, capital F of x is equal to x cubed divided by 3 is the antiderivative of little f of x being equal to x squared. You can test that. Antiderivatives you can always test. Take the derivative with regards to x of this thing, capital F of x. Well, that's the derivative with regards to x of 1/3 of x cubed, which is by the power rule, this power comes down, and we subtract 1 from the new exponent. 3 times 1/3 is 1. Then we would get x to the 3 take away 1 is 2. We got back to where we started. So, capital F of x, which is equal to 1/3 of x cubed, is an antiderivative to this lowercase f of x. But what about this g of x, where we just add a constant 1? If we take the derivative of g of x, g prime of x is still little f of x. And what about h of x? Well, once again, if we take the derivative of h of x, we will get this little lowercase f of x. So an antiderivative is not unique. One function can have infinitely many antiderivatives. Remember, all this antiderivative does is it gives us the slope of this function at a point. And it doesn't matter how high or low it's been shifted, the slope is the same. And I've got a graph on Desmos that will hopefully help illustrate this idea. So let me cut over there real quick. Okay, so here I have the graph y is equal to x squared. And first off, I'm going to put f sub 4. I needed to give them all a bunch of names, so don't worry about the f sub 4. That's equal to 1/3 of x cubed. So we have this 1/3 of x cubed, and this straight line is the tangent line, or is the line tangent to 1/3 of x cubed at a point. Our point's off the graph right now, so let's bring it back. Perfect. So this line is the slope of the tangent line at this point. And the slope of this tangent line is given by y is equal to x squared. But what I was saying was this equation, f of x is equal to 1/3 of x cubed plus 1, if you look, has the exact same slope at every single point. And same with this function and this function, and this function and this function and this function. For the same value of x, all of these lines have the same slope. Notice how they're always parallel. Since they're always parallel, their slopes are the same. So without having to see them, and I'll show them to you, we just changed their y-intercept, -3, -2, -1, 0, 1, 2, and 3. All of these lines, all of these 1/3 x cubes are just vertical shifts from each other. But the thing is, just because they've been shifted vertically doesn't mean their slope has changed. So, if notice, I don't know the right word to say there, take a look at how y is equal to x squared gives the slope of all of these functions for a certain value of x. Antiderivatives are not unique. Any function any function, this y is equal to x squared, has infinitely many antiderivatives. And all that is because you can shift its antiderivative up or down by a number and it doesn't change its slope. I can take this f1 and I could shift it up instead of by 3 by 30. And the slope is going to be the same. So, let's go back to the paper. So what I just said can be formalized into a theorem. If capital F is an antiderivative, of lowercase f on I, then the most general antiderivative of f on I is, of lowercase f on I is capital F of x plus some constant, where C is an arbitrary constant. So that's like, so back to our previous example of x squared and 1/3 of x cubed. That's why when we have lowercase f of x being equal to x squared, we can have an antiderivative being 1/3 of x cubed plus 1. We can have an antiderivative, I'll call it g of x, being 1/3 of x cubed minus 100, or some h of x being equal to 1/3 of x cubed plus 17. So what this theorem is saying is, so if f is an antiderivative, so if f is an antiderivative, just any of them, is an antiderivative of f, x squared on I, then the most general antiderivative of f is equal to x squared is 1/3 of x cubed plus some constant, where c is an arbitrary constant. So this is our idea. Let's do a couple antiderivatives. So, example 1. We're going to find the most general antiderivative of each of the following functions. So the first is A is f of x is equal to the sine of an x. B is f of x is equal to 1 over x. And then C is f of x is equal to x to the n, where n is something different than -1, but a real number. So, when coming up with an antiderivative, that was supposed to be an A, not a 9 or Q or whatever I was trying to write. A. So, in coming up with antiderivatives, you really ask yourself, the derivative of what function is sine of x? And then you have to go through your catalog of derivatives you have stored in your mind, and you go, okay, we're dealing with trig stuff. Usually derivatives of trigs is equal to something that's also a trig function. I know that the derivative with regards to x of cosine is equal to a negative sine of x. That means that the derivative with regards to x of a negative cosine of x is equal to a sine of x. Cool. But the derivative with regards to x of negative cosine of x plus 4 is also equal to a sine of x. And the derivative of negative cosine of x, and I should put brackets here, minus 11 is equal to the sine of x. Perfect. So the antiderivative of sine of x would be a capital F. The antiderivative of sine of x is going to be this negative cosine of x plus some constant. Your answer would be capital F of x is equal to a negative cosine of x plus c. And you have to write the plus c. Have to write wrong without. Forgetting to write the plus c is like forgetting to write the limit when we're evaluating limits. You have to write the plus c when we're doing these general antiderivatives. Okay, so what about f of x, lowercase f of x, and this is b, f of x is equal to 1 divided by x. Can you remember a function whose derivative is 1 over x? Well, capital F of x is going to be the natural log of, this is where it gets tricky, the absolute value of x. Perfect. So there's one condition. We need that plus c. You forget that plus c. It's typically worth a half a point. And we have to have some condition. X can't be equal to 0 because we can't take the natural log of 0. Okay. But the antiderivative of 1 over x is the natural log of the absolute value of x. Finally, we have the x to the n. If f of x is equal to x to the n, well, the derivative with regards to x to the n is equal to n times x to the n minus 1. So we want to come up with something whose derivative is equal to x to the n. Okay, so, and we will formalize this into an official rule in a second. But the antiderivative of any x to the n, where n is different than negative 1, is x to the n plus 1 divided by n plus 1. Now, take a second to convince yourself of that. And by take a second to convince yourself of that, what I'm telling you to do is take the derivative with regards to x of x to the n plus 1 divided by n plus 1. When we take this derivative, the power will come down, and we would subtract 1 from the new power. That would give us n plus 1 divided by n plus 1 times x to the n. N plus 1 divided by n plus 1 is equal to 1. We know that n is different than negative 1, so this is just x to the n. Okay, I don't like to give you guys formulas. This is definitely something that should become muscle memory. Kind of like how taking the derivative of x to the 17th should be slowly becoming muscle memory. Now think about it going in the other direction. For your antiderivatives, like I wrote on the back page, the derivative of what function is sine of x, or the derivative of what function is 1 over x, or the derivative of what function is x to the n. So there's also a good table of antiderivatives on page 352 of our book. Good table of antiderivatives. On page 352. Once we get into chapter 5, we will call antiderivatives a different name, and there will be other tables in your book you guys can use. But for now, a table of just antiderivatives is on page 352. So for our second example, we want to find all functions g such that its derivative is equal to 4 times the sine of x plus 2x to the fifth minus the square root of x divided by x. So at first, this might seem kind of intimidating, like we've got a quotient rule floating around. You can algebraically manipulate your derivative. So by algebra, g prime is also equal to 4 times the sine of x plus 2x to the fifth divided by x is 2x to the fourth. We're going to minus the square root of x divided by x is equal to x to the negative 1 half. Okay. So now we want to come up with some function g that when we take the derivative, we get the thing above. Well, constants we can pull in and out of derivatives. We're going to get 4 times the derivative of what is sine of x? Well, a negative cosine of x. And then we're going to add 2 times the antiderivative of x to the fourth is what? We will get x to the fifth divided by 5. And then we're going to subtract, then we're going to get x to the 1 half divided by 1 half. And then we get a plus c. Don't forget about your plus c. You guys are inevitably going to forget about your plus c. You don't know how many times I re-recorded example 2 because I forgot my plus c. Don't forget your plus c. So at this point, we're just going to rewrite this equation, make it look a little bit better. We're not going to divide by fractions. We get g of x to be equal to a negative 4 times a cosine of an x plus 2/5 of an x to the fifth minus 2x to the 1 half plus some constant for our final answer. But antiderivatives are hard. Especially when you've done a bunch of them, especially when you're in Calc 2 and it's not exclusively dedicated to antiderivatives, but it's a good portion of what you're going to learn in Calc 2. You can always check. We know that the derivative with regards to x of g of x should be g prime of x. And this is kind of our roadmap for checking. We want to take the derivative with regards to x of g of x. Negative 4 times the cosine of x plus 2/5 x to the fifth minus 2x to the 1 half plus c. And when we take the derivative term by term, the derivative with regards to x of negative 4 cosine of x is a 4 sine of an x. Plus, our power would come down 5 divided by 5 is 1. That would leave us a 2x to the fourth. And then we're going to minus, our power would come down, 2 times 1 half is 1, times x to the negative 1 half, and the derivative of a constant is 0. And we want to check that we got back to where we started. You can always check your antiderivatives by just taking a derivative and making sure you got back to where you started. Perfect. So, let's go through and do another. So we're gonna do something new in this problem. First off, example 3, we want to find lowercase f if f prime of x is equal to e to the x plus 20 times 1 plus x squared to the negative 1, and f of 0 is equal to negative 2. Okay, so we have this function. We have f prime of x, and once again my print and my cursive is the same thing. My lowercase and my capital would be different. F prime of x is equal to e to the x plus 20 times 1 over 1 plus x squared. So the derivative of e to the x is just e to the x. So we've got an idea on what to do here. This 20 is a constant, it's going to fall down. But the derivative of what function is equal to 1 over 1 plus x squared? That is the tan inverse of an x. Okay, so this is how we're using our derivatives to come up with antiderivatives. This means f of x is equal to, well, the antiderivative of e to the x is e to the x plus 20, and the antiderivative of 1 over 1 plus x squared is the tan inverse of an x. We're taking antiderivatives, so we get a plus c at the end. You can always go back. The derivative of e to the x is e to the x. The derivative of 20 tan inverse of x is 20 times 1 over 1 plus x squared. The derivative of a constant is equal to 0. So this is what we've done up until now. This is the new part. We now know what f of x is. Well, that means f of 0 is going to be equal to e to the 0 plus 20 times the tan inverse of 0. And we know this thing is equal to plus c plus some constant is equal to negative 2. That's a c. And that's a plus sign. You're going to forget your plus c at some point. What we're trying to do now is we're trying to figure out the value of plus c. Well, we know e to the 0 is equal to 1 plus 20 times the tan inverse of 0. The tan inverse of 0 is 0 plus some constant is equal to negative 2. That's equal to 0. 1 plus c is equal to negative 2. That means c is equal to negative 3. Now, we know what c is. We have gone from a general antiderivative to a specific one. Oh, my pen is dying on me, I think. Nope. 20 tan inverse of x minus 3. So, now we have a specific antiderivative. We were given some initial condition. That allowed us to lock in on one specific antiderivative. Perfect. So for example 4, we want to come up with some function whose second derivative is equal to 12x squared plus 6x minus 4, and where f of 0 is equal to 4 and f of 1 is equal to 1. Perfect. So first off, let's come up with the first derivative of f. If f double prime of x is equal to 12x squared plus 6x minus 4, well, the first derivative of f has to be equal to, and I'm going to do this one a little faster, 12x cubed divided by 3 plus 6x squared divided by 2 minus 4x plus some constant. Okay? One a little faster. We added 1 to our exponent divided by the new exponent. Added 1 to our exponent divided by our new exponent. We gave that one a variable, and we found this constant somewhere. I am going to just simplify. F prime of x is equal to 12 divided by 3 is 4x cubed plus 6 divided by 2 is 3x squared minus 4x plus some constant. So, now that we have f prime, now we need to come up with f. Well, same idea. F of x is equal to, and I'm going to go faster, 4x to the 4th divided by 4 plus 3x cubed, cubed divided by 3 minus 4x squared divided by 2 plus cx plus d. Now, when I wrote this in my lesson plans, I called these C1, and I called this thing C2, constant 1, constant 2. I am personally a big fan of subscripts. That's just because in my mind, C is a constant. It's a different constant, but it's still a constant. You can either call it C1, C2, you can call it C or D. Whatever you call your constants is up to you, really, just as long as you know it's a constant, and you know that the antiderivative of a constant is that constant times x. So, we're going to simplify. F of x is equal to 4 on 4, x to the fourth plus x cubed minus 2x squared plus cx plus d. Now we have two initial conditions. The one that is f of 0, this one is typically the easiest one. I would recommend you start. If you know what f of 0 is, start with that one. F of 0 is going to be 0 plus 0 minus 0 plus 0 plus d is equal to 4. We get d is equal to 4. F of x is equal to x to the fourth plus x cubed minus 2x squared plus cx plus 4. F of 1 is 1. F of 1 is equal to 1 plus 1 minus 2 plus c plus 4, and that's equal to 1. 4, 5, 6, take away 2 is 4, so we get c plus 4 is equal to 1. That says c is equal to negative 3. Combine that with what we had, and we get f of x is equal to x to the fourth plus x cubed. Oh gosh, I've written off the screen. I'm sorry. X to the fourth plus x cubed minus 2x squared minus 3x plus 4. Sorry, I'm using a document camera now. So we started off with what we had, and we went term by term. To take the derivative, or to take the antiderivative of an x to the n, you just add 1 to the exponent, divide by new exponent. So we went from 12x squared to 12x cubed divided by 3, 6x squared divided by 2 minus 4x. Don't forget to add your constant. Doing some algebra to simplify some things. If they gave us information about f prime of x, we could use that here, but they didn't. They only gave us information about f of x, so we had to figure out our values of our constants down here. We integrated term by term. We found the antiderivative of each term. We won't use the term integrated until next chapter. Antiderivative, 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 plus a new constant. Don't call it c. This constant isn't necessarily the same as this constant. As we found out here, they had different values. So I don't care if you call it C and D. I don't care if you call them C1 and C2. Just don't call them both C. If you call it C and then you call it D, I would not recommend the next variable you choose be E, just because E is a number. I also wouldn't recommend you guys use F, G, or H, because typically F's, G's, and H's get used for functions. But I'm not going to tell you what to call your constants. You can call your constants whatever you want to. C, D, C1, C2. I'm a fan of Greek letters. If I was doing calculus for myself, I probably would have called that a lambda or something like that. I like lambdas and gammas. But we go term by term. Once we have this wonderful function with arbitrary constants floating around, we have to use the information that was given to us. I like to use f of 0 is equal to some number first, because that gets one of these to just go away. It makes life easier. Doesn't always work. Solving for these constants can get kind of tricky. There can be techniques that you'll have to employ in order to do that, but for now we're trying to keep things fairly straightforward. Perfect. Let me get set up. Okay, so for example 5, the graph of a function f is given below. Make a rough sketch of an antiderivative f given that f of 0 is equal to 2. So this is f. This is the derivative. The rate of change, or the slope at each point. And there's some information we can get from the derivative. Well, right here, and I'll give this a value of 1. We'll say this is at 2. We'll say this is 3. And we'll call this point 4. So on the interval from 0 less than x less than 1, we're going to be decreasing because the derivative is negative. Where the derivative is 0, we have a critical point. I'll just call it CP. And then we, over this interval from 1 to 3, we're going to be increasing. 1 less than x less than 3, we're increasing. And when x is equal to 3, we're going to have another critical point. When x is equal to 2 and x is equal to 4, we have inflection points. And so we're going to decrease from 0 to 1, we're going to increase from 1 to 2, and then we're going to decrease forever. But notice the rate at which we decrease goes to 0, so we're flattening out as x gets really large. So we also know that f of 0 is equal to 2. So let's start here. When x is 0, f is equal to 2. And then we're going to decrease for a while. We're going to decrease. We're going to hit a critical point, and then we're going to increase until we hit another critical point, and then we're going to belly out. So this is where we have this critical point, where we have a horizontal tangent line. We have another critical point here. To the best of my ability, we will use our imagination so that we have a horizontal tangent line there as well. We're decreasing, we're going down on this interval, we're increasing on this interval, and then we decrease forever, and the rate at which we decrease goes to 0. We get this horizontal asymptote. There's a lot of different functions you could draw. Remember, sketches aren't precise. The overall, and we can get an idea about our slope, or we know exactly our slope here. But I mean, it's not wrong per se to drag that thing down. And get that function. This too could be some capital F. So you have to be careful. Once again, the important word is sketch. You're going to be asked to do this, and this is an exercise of getting you guys to think visually about what information the derivative can give you about parent functions. I was when I took calculus, they called antiderivatives, or the family of antiderivatives, parent functions. Okay, so moving on to another example. So for linear motion, and by linear motion, we're talking about particles that move forward or move back in a straight line. They can zigzag back and forth, but they're moving in just a straight line. So antidifferentiation is particularly useful in analyzing the motion of objects moving in straight lines. Let me get my next piece of paper, and we'll be right back. Okay, so for example 6, we want to find, a particle moves in a straight line and has acceleration given by a of t is equal to 6t plus 4. Its initial velocity is negative 6 centimeters per second, and its initial displacement is 9 centimeters. Find the position of the function. Find the position function, I'm sorry. So we have the displacement, s of t. And we know at the start of our model, at 9 centimeters away, we have this particle, and it's moving backwards with the rate of negative 6 centimeters per second. So, given this information, we'll figure out what s of t is. We're given that a of t is equal to 6t plus 4. We know that acceleration is the rate of change of velocity. So we know if we find the antiderivative of acceleration, that'll give us velocity. That'll give us 6t squared divided by 2 plus 4t plus some constant. We can simplify. V of t is equal to 3t squared plus 4t plus c. Now, we were given this information about the initial velocity. We know that its initial velocity, its initial velocity is when t is equal to 0. So that means v of 0 is equal to 3 times 0 squared plus 4 times 0 plus c, which equals -6. 0, 0, this tells us c is equal to -6, or that our velocity function is actually 3t squared plus 4t minus 6. I believe this is the first example that we've done where we haven't gone all the way to the end and then found out the values of our constants. If they give us information about one of the derivatives, we'll use that derivative to figure out missing information. Use what you're given. So, we know that the rate of change of position is velocity, so that means our position function is the antiderivative of velocity. That would give us 3t cubed divided by 3 plus 4t squared divided by 2 minus 6t plus some constant, which I will call d. I don't want to, I have ran out of space, so going on the back, I'm going to rewrite s of t. S of t is equal to 3 divided by 3 is just t cubed. Oops. We get plus 4 divided by 2 t squared plus 2t squared minus 6t plus d. And we know its initial displacement. Its initial displacement is equal to 9. 0 cubed plus 2 times 0 squared minus 6 times 0 plus d is equal to 9. All of these terms are equal to 0. That tells us d is equal to 9. The position of this particle is given by the equation t cubed plus 2t squared minus 6t plus 9. So, use the information that's given and apply it when you can. We were given some information about velocity, so we were able to solve for one of our constants working exclusively with the velocity equation. Then we knew stuff about the displacement, so we used our equation that modeled displacement to find a missing constant. Use what you were given to figure out what you need. Okay, so for our final example, a ball is thrown upward with a speed of 48 feet per second from the edge of a cliff 432 feet above the ground. Find its height above the ground t seconds after, find the height above the ground t seconds later. When does it reach its maximum height? Okay, so there's two bits of information that we need. Well, one kind of said differently. The force of gravity is constant, and it's either equal to 9.8 meters per second squared or 32 feet per second squared. This problem is given to us in feet, so I'm going to use the 32 feet per second squared. If you guys go on and take a calculus-based physics class, I assume everything you do will be done in terms of meters per second. So, let's begin. So, gravity is a force of acceleration that is acting down. So, this ball, its acceleration is going to be given by -32. Since gravity is a constant force down, it is constantly being pushed down at a rate of 32 feet per second squared. That means our velocity at time t is going to be equal to -32t plus some constant. But we know we were thrown upward with a speed of 48 feet per second. This is our initial condition about velocity. What this statement says is that v of 0, which is -32t plus c, has to equal our initial velocity, 48. That means our constant is equal to 48, and the equation that models our velocity as a function of time is negative 32t plus 48. Cool. So now at this point, we can actually answer some information. I'm going to just copy what we have here. We have a of t being equal to negative 32. We have v of t being equal to negative 32t plus 48. What we want to do, one of these things we want to do in this problem is find the maximum height. Well, what we're going to do is, finding the maximum height is going to be when the velocity equals 0. We're on the edge of a cliff and we're throwing something up. Once that velocity equals 0, that's going to be our maximum height. So we can already take our velocity equation, set it equal to 0, and that'll give us t is equal to negative 48 divided by negative 32, which when everything clears out, that'll give us 1.5. So we know when t is equal to 1.5, our velocity equals 0. So we will take this bit of information, and in fact, find its height above the ground t seconds later. When does it reach its maximum height? This is kind of the answer to that second question we were asked. So now we need to find its position function, the first thing we were asked. Well, its position as a function of time, antiderivatives, we'll get negative 32t squared divided by 2 plus 48t plus some constant d. Well, we know that it was thrown from 432 feet above ground. So that means at time 0, 0 plus 0 plus d, we're 432 feet above the ground. That tells us d is equal to 432, which lets us know that our position as a function of time is equal to negative 32 divided by 2 is negative 16t squared plus 48t plus 432. Perfect. So this is our position as a function of time, and this is how long it'll take for us to reach our maximum height. We can confirm this suspicion. We can confirm this position. We'll figure out what its maximum height is. And when does it reach its maximum height? Perfect. So, like I said, this is our position function. When we're trying to figure out what its maximum height is, we want to figure out what its position after 1.5 seconds is. Negative 16 times 1.5 squared plus 48 times 1.5 plus 432. Let me grab my calculator because I forgot to get us that number. 1.5 squared times a negative 16 is a negative 36 plus 48 times 1.5 is a 72 plus 432 is equal to a 468. Perfect. So it takes the ball 1.5 seconds to reach its maximum height of 468 feet. So antiderivatives. My primary concern is with you guys being able to go from A to V to S. We're going to do a lot of dealing with stuff with initial conditions. Dealing with your initial conditions really is a Calc 2 sort of thing. You guys will get plenty of practice in Calc 2 doing that. So, let's see. That's really the big one. For coming up with antiderivatives, you ask yourself the derivative of what function is equal to the thing you're being presented with. Sometimes, for some problems, you'll have to come up with two antiderivatives like you've seen. With regards to gravity being a constant negative force of either 9.8 or 32 feet per second squared, I would give you those numbers in a problem. It's something that you guys will eventually have memorized, but I'll give it to you for what we're going to be doing. For homework, go off and do 1 through 21 every other odd, and 25 through 45 every other odd. This wraps up the Chapter 4 material. We will have our Chapter 4 test this weekend. And send me an email if you guys have any questions. Take it easy, everyone. Bye-bye.